All right, now we're entering into part 5 of Data Analysis 2, Regression, and this will be a little bit of a longer section. All right, so regression is a common and fundamental technique to model a relationship between my preferred terminology of a response variable and one or more explanatory variables, right? So this makes it clear that response is what we're interested in. That's the thing that's reacting, and we have other variables that come in to explain the response. However, a lot of literature will call the response variable the dependent variable and the others the independent variables. Sometimes the response variable is the outcome variable and the others are predictor variables. But I'll try to stick to response and explanatory as my preferred terminology. So, typically you take a whole course on regression because the proper implementation of it requires not only just running these commands that we're going to see, but requires attention to how the model fits, how we select variables, issues that arise with the residuals and variance, and many methodological refinements, because what we're trying to do is find an explanatory model that fits the data well, and we have to have some evaluation and judgment on that. But this is the quick and dirty way just to show you the R code that will accomplish the first steps in this process. So the simplest kind of regression, linear regression, or what's sometimes called OLS, or ordinary least squares regression, is accomplished with LM in R. And I'm going to again toggle back over to my RStudio window. I'm at line 355 right now. So we say LM, and we put in our parentheses the variables we're interested in. First comes the response variable, and then this little tilde squiggly symbol that lives at the top left of many keyboards. Everything to the right of that are going to be explanatory variables, one or more explanatory variables. So here I'm asking for female labor force participation as it relates to GDP per capita. And when we run that, we get this result that's just the coefficients. A 4.685 to the minus 04. Now remember that GDP is in thousands, right? So it's basically 0.468 per thousand. The labor force participation increases, or is that 10,000? If one of the other, if I may not be reading the notation correctly, and an intercept of just 5, right? 5% in this case. So yeah, 0.5 increase in the labor percentage participation for every $1,000 rise in GDP. But if you have looked at most regression results, they're usually not as sparse as this. It's another quirk of R that some functions we have to enclose in a summary command. So we put summary parentheses and then stuff the entire LM linear regression function inside the parentheses, and then we get what I would call a more normal complete display of results, which shows us not only the coefficients but the standard error, the t-value, the p-value, the significance level, right? So this is one of the first steps of judging, is this a meaningful regression? The coefficients should at least have statistical significance, otherwise they are not distinguishable from randomness as a result. We also get things like the R-square, which explains how much this model explains of the complete variation in the data. and other useful information. Yeah, and actually I'm looking at what I've written here, and what I've written here is based on the previous data. I think the gender data has been updated since this was written, and because now the significance level is just below 0.05, where I was saying it was not significant at the 0.05 level, now it is. So there's been a little update here, which I'll just go ahead and make that change now. Now significant. Okay. That's probably a good enough edit. So let's check some other relationships. We will check labor force female participation versus fertility, and then fertility versus GDP, sort of studying the cycle among all these things. So fertility rate definitely influences labor force participation. A higher fertility rate means lower labor force participation, and a higher GDP means a lower fertility rate, right? They're all connected, all have similar p-values, interestingly, like all just below 0.05. And another thing to know about running a regression is if you don't want an intercept, you put -1 at the end of the equation. So sometimes we want to model something where, at 0 it's 0, and then see where it goes from there. And even with this constraint of no intercept, labor force and GDP are significantly related. Okay, multiple regression is actually very simple in R. We simply add a plus and add an additional variable, and we can have as many variables as we like. Fitting, right? Adding a variable will always increase your R square, will always look like it's explaining more because it's just extra information that can be used to improve the fit wherever the first variables that you put in didn't do well. There's going to be some extra little something in the variable you add that improves the fit. But there's such a thing as overfitting, where we can keep adding things. We can add the cloud pattern on January 17th to the data, and it might randomly match up on something, right? The math is such that it will always use that information to increase the R square. But we have ways to analyze whether it's really worth it. Are we getting enough of an improvement by adding that variable to justify putting it in? And those are things like the AIC, the Akake information criterion, which we won't again really go into further here, but just so you know that these are some of the considerations in regression. Now, an important feature, non-theoretical feature of regression in R, but just a practical feature, is that we can store these regressions as sort of abstract data objects. And that lets us do a lot of things with them that we can't do in other stats languages. So we just use R's assignment operator language. I'm looking at line 403 right now. And we type that less than sign and then a hyphen, right? That's the assignment operator is called in R. It means whatever's on the right-hand side of the arrow gets put into what's on the left. So we just have our linear regression formula, and we put it into something called reg output. Now, once we do that, it exists in the workspace. You can see it over here in the top right, reg output, list of 12 things. We can even click on it and take a look at those. We have all the coefficients of the regression, all the residuals, all the fitted values, some other information like the degrees of freedom and the rank and description of the model and the formula. It's all at our fingertips now to be used in different ways. And we can use it just like we use other R variables by saying reg output $, and then the name of one of these elements. So reg output $, residuals prints out all the residuals from this regression model. And because we can store them, we can run multiple models and compare regressions 1 through 10 or 1 through 100, and look for the ones that have certain nice fitted values or have certain well-behaved residuals, or feed all that information together in lots of different ways. Also, once you have this regression output as an object, you have these quick functions that work alongside them. So you can just say predict reg output or ANOVA reg output, and that's a quick way to pull up the predicted values. There are ways to just actually quickly insert that into a plot. ANOVA gives an analysis of variance table, which is one way of looking at the how much of the variation can we explain by using specific variables. And it quickly gives you that presentation. And we can also do a plot of the regression, which is coming up in a minute. Actually, that's a little later, so let me wait on that for a second. Okay, so a little bit more theoretical discussion. I mentioned in the beginning, I'll go back to the web page view, since they're the links, I like the way they display here a little bit better. That when we don't just mindlessly run a regression, we want to evaluate it. And this whole field is called regression diagnostics, whole field of activity. So we might want to test one thing, which is the normality of the residuals, right? If the residuals are not well behaved, as we say, it may be a sign that the linear fit is not the best fit for the model. But if they are normally distributed around our fitted line, that means that the variation is kind of, it's random, and our line fits as well as we can hope it to fit. I've linked to some articles that explain what goes on behind this in a little bit more detail, but two things that are often tested for are the Shapiro-Wilk test and the Kolmogorov-Smirnov test. Right. So we use these with what we call standardized residuals, meaning we scale the residuals to a common basis. We divide by the standard deviation, and that way we can compare residuals with a mean of 0 and a standard deviation of 1, no matter what the environment is. So a lot of these tests want the input to come in that form. So for example, the Shapiro test, we process the residuals of reg output simply by saying our standard reg output, and then say Shapiro test. Now the Shapiro test has its own presentation. If the data has a significant p-value, then we reject the null meaning we reject that the residuals are normally distributed. And again, that's a sign of a problem, right? A problem that the linear model is not a good fit. We need to look at other things. If we have a p greater than 0.05, we're okay. We have passed this test in the sense that we don't need to worry about fitting a different kind of regression model. These two tests, the Shapiro-Wilk and the Kolmogorov-Smirnov, are really doing the same kind of thing. Shapiro is more commonly used, I guess I would say, and the Kolmogorov-Smirnov test does the same kind of thing, but it is the formulation is a little more general. The Kolmogorov-Smirnov test can be fit with different distributions. And you notice in the syntax here we specify p norm, like we're actually specifying, let's use the normal distribution. We expect the residuals to fit a normal distribution. We actually have the option of specifying a fit of other distributions if there are cases where that makes more sense. However, we also need to be a little careful, right? When we run this command on line 434, we get a significant p-value. Like, oh, okay, what's going on? We should reject the null. We should say these residuals don't fit nicely. That's because we really need to be careful. We used standardized residuals with this rstandard function. And let's standardize both the residuals and the distribution we're matching it to. So we refine what sort of went wrong on 434 by saying rstandard reg output, p-norm as the distributional model, and a mean of 0, standard deviation of 1. Once we do that, then we have a p-value as we would expect. We would expect to get the same kind of result, except in the case of maybe really close calls from Shapiro-Wilk and Kolmogorov-Smirnov. So in this case, now we've been more precise about the syntax, and we have normally distributed residuals indicated by both tests, right? And then I had mentioned the plotting earlier. The plot is simply the command plot with reg output inside, and this will give us a nice set of 4 diagnostic plots that, without going into detail, right, we in general want these plots to fit to the lines indicated, not show large deviations, and these are the types of things we look at to evaluate, does the regression model fit well, and even to locate specific places, outliers, points in the distribution that cause problems. And that's accessible, again, just plot. The PCH is the printing character, which can be modified to your tastes if you want some other look to those graphs. There are 20 printing characters, so you can experiment with the different numbers there. So that was all about linear regression. There are many other modifications, different kinds of regression. We're just going to look at logistic regression as one other type here, because that's also very commonly used. And it's implemented with the GLM command, which is generalized linear models. So as that statement implies, generalized, GLM can do other things beyond logistic, but we're just going to look at the logistic variant here. So I've given you some links. You can read about the package. There's actually two, as there often is in R. There's GLM and there's GLM2, right? So someone's written a revised different version of I don't have an opinion on whether you should be using GLM or GLM2. You can experiment with that. So what is logistic regression? If you're not familiar with that, that's when you have the response variable is categorical, typically like a yes or no, true or false, 0, 1, binary as it's called. So does someone vote yes or no on a specific issue? Are they for or against X? So we model that with a distribution that has a transition point, right? People who have a certain bundle of characteristics tend to vote no. When they cross a certain threshold, they switch and they are likelier to vote yes in that example. But we have to, that's not linear, right? We model a kind of S-shaped transition, and the appropriate statistical distribution is the binomial distribution, because we're, instead of having values that are centered on a certain point and can deviate, it's only 0, 1, right? 0, 1 responses that happen. In some circles, the 0, 1 coding is referred to as one hot coding. I have no idea where that language originally comes from. I'd be curious if someone has the answer to that question. All right, so enough about the background. You can read more about logistic regression separately. Just to show you that it's very similar to the syntax for regular regression. We're still using the tilde. Here I'm asking for, is the female labor rate high? Remember we said 70% and above is high labor participation. Is it high or not? As explained by fertility plus GDP. Those two explanatory variables. And we simply say family equals binomial to indicate that we would like to use that style of regression that generates a logistic regression. And then we look at the summary of logistic output to get this full table of results. So we also have p-values. In this case, none of the coefficients are significant. Again, we have a small data set. The interpretation of the coefficients is quite different. It actually reflects the odds of a change in that variable influencing the switching of the yes, no, 0, 1 result. But otherwise somewhat similar to the linear regression. We don't have things like the R-square concept doesn't apply here in the same way. But this is normal logistic output. And again, R is built for statistics, so everything you've read about and heard of, there's pretty much going to be a way to do it in R. All right, and so this is another case where I want to show you the Python version. So Python regression comes not in NumPy or SciPy, but comes out of scikit-learn. Let me just go to this section in the web view. Scikit-learn is maybe the premier module in Python, the one that has all the machine learning stuff. So if you have touched Python, you might have touched this part of Python. Again, I'm going to give you a quick and dirty example just to show you that this is possible. There are other guides out there. I'm not also even claiming that the ones I'm linking you to are special in any way, but I found them. And so here's a guide that talks about implementing regression in Python, along with some of the issues, kind of walk you through that. So if you look at this content and you say, oh, I really prefer to do this in Python, you have some tools. Python, as we have seen earlier, doesn't give you like the normal, it just by default doesn't present the output. So there are these modules that I have read about. Again, I'm not really a in practice Python user, but Stargazer and Stats Models are two approaches to actually getting your Python to behave like I'm simply going to say more like R, and give you some default results. So Stargazer lets you produce these little tables from your regression, including this nice like LaTeX version tables. So definitely has a use. Stats Models has the same kind of thing. Again, extracting and formatting your regression results in a way that is well behaved. And R also has these packages. I haven't even really gone down that road to explore those, but there are certainly many options to export and format your R tables as well. I don't want to give the impression that that's not possible. All right, but now let's run this to make sure that we see this in action. This is really the same thing that we saw in part 3. We've got a chunk of code labeled Python. We have straight up Python code for everything here except this data import part. And that's exactly the same as in part 3. We say R dot and then the name of the data in R, mapping it to gender Python on the Python side. Here I extract two variables, the labor and the GDP. It's necessary in here to reshape the data into what I'm calling here Python friendly form. That's just a sort of technicality about the way the matrices and vectors line up. This is the stuff that me personally, I'm used to the R world, and I find it very odd in Python that some of these, like to me, R handles the math side very naturally, and Python is more like, oh, we have to have these little workarounds to make the math work. I'm sure that people look at R from the computer side and find many things clunky in R as well, but this is one that, anyway, it has to be done in Python to make our regression come out. So we use this linear regression from scikit-learn. We run this fit of the model of these two variables against each other, and then we can print the results from the model, referring to specific variables that are produced. R square, we have to specifically request that as the model does score, things like that. This is what you have to do manually if you're not using those like Stargazer or packages like that. Okay, let me just go ahead and run this. And once again, it has entered into the three caret Python mode. That's how we know it's in Python mode. We see those steps running. We see on the right, we see all of these things being generated in the Python workspace. I didn't mention this before, but the environment has now two components, right? It has a Python side and it has an R side, right? So things are either in the R space or they're in the Python space. That's why we have to have that step to pull the data from R into Python. But it does work. We have an intercept and a coefficient, not printed very prettily, but negative 25,000 with a coefficient of 716. And we are regressing the GDP here against the labor force, right? So the minimum labor force participation is high enough to overcome the negative 25,000 of GDP, right? And R square is reported there as 0.34. Okay, so we can accomplish those things in Python. To become a master of regression in Python is a little bit different of a toolkit, I would say, than in R. And it would really depend on your goals. If you want to have all of the statistical options available to you, R is the way to go. If you want to integrate standard regression results into a machine learning pipeline, things like that, Python can be the way to go. And of course, now you can mix and match. Right? You can run some procedures in R, pass the data to Python, and vice versa, and have the best of both worlds. Okay, that's the end of part 5. Thank you for your attention so far. And I will return with the final section, part 6, on the Bootstrap.